Kia ora and welcome to this video on question 4 of the 2017 Scholl Calc exam. Three parts to this question. The first involving a messy integral, but they give you the answer. And so we're going to use a differentiation approach to solve this problem. 4b, an unfamiliar integral that involves finding the length of a polar curve. And then third, a pretty nasty differential equation by scholarship standards, but it is 4C, so it's expected to be a little bit more challenging than earlier questions in the paper. Alrighty, question 4A. This is a typical problem in scholarship where they give you the integral with the answer, and actually integration is not expected to be able to solve this. Like, how the heck would you integrate a triple product of things? It's like integration by parts to the next level, like 3 functions. I don't know. But because they've got the answer, we can differentiate the answer. If we can differentiate the answer and show it equals tan x, tan 2x, tan 3x, then we've made the proof. If you're looking at the integral and you want to know how to do it using integration, look at the mark schedule because they do. But personally, I think it's easier to differentiate than it is to integrate. So, the derivative of the right-hand side, d dx right-hand side, is 1 over cosine times minus sine. Remember, log differentiates to 1 over, but it's 1 over something times something differentiated, plus a half times 1 over cos 2x times the derivative of cos 2x minus 2 sine 2x, and lastly minus a third times 1 over cos 3x times negative 3 sine 3x. Kind of weird that there's a minus and the other two terms don't, but it turns out that's how we prove it. Tidying this up a little bit, sine over cosine is tan, so we've got minus tan. The half there cancels with the 2, third there cancels with the 3. We end up getting minus tan 2x plus tan 3x. It looks like we're wrong because the left-hand side that we're aiming for is a product, and we've got a sum. So we can change tan 3x, and I've done this in an earlier video, but if we go tan of 3x is tan of x plus 2x, which is tan of x plus tan of 2x over 1 minus tan of x, tan 2x. It's the compound angle formula. And if we rearrange this equation by cross multiplication, therefore tan 3x times the denominator is equal to the numerator, then we can see that tan of 3x equals tan x plus tan 2x minus tan 3x, tan 2x, tan x. Okay, so that's what I'm going to replace. So continuing, left hand side, d dx left hand, oopsies, it wasn't left hand side, it was right hand side. Doesn't matter. Minus tan x minus tan 2x plus this stuff. Okay, and we've got some cancellation, and we're left with, where's the minus come from? Oh my goodness, when you put it on the other side of the equation, that should be a plus. Plus. If you've been following my earlier videos, you'll know I make lots of mistakes often, but the key to a good exam is being able to spot those mistakes in your exam and correct them. Okay, so that equals the right hand side without the integral, so that's a proof. Okay, question B. The length of a curve expressed in polar coordinates is given by the following equation. You can derive this if you're interested. On the internet you can find it, but what it's saying is from the origin, this here is r. And so r is changing depending on what theta is, and theta is this angle. So r is a function of theta. It turns out for this particular curve, r is always positive. Okay, well in fact in polar coordinates, r is a radius, so yeah, positive. This function here is positive except for at the origin when theta is 0 and when theta is 2 pi when it's gone back done a whole revolution. And because of that, we don't have to worry when we integrate about splitting the integral up, and the thing we're integrating is a positive square root of a quantity that's always positive. So we can just integrate straight from 0 to 2 pi. Looking at the answer schedule, they split it from 0 to pi and double it, but we don't need to do that. Okay, so we're integrating the square root of r squared plus dr d theta squared d theta. The proof of this formula considers like a small, that I've drawn it purposefully big, a small line segment where that's d theta and this here is like ds. It says what happens if you add up all of the small line segments. But yeah, don't worry so much about that one. Okay, so we want to integrate it from the start to the finish. So from theta equals 0 to theta equals 2 pi. And we know that r is equal to a times 1 minus cos theta. So what we need to do with this is replace the r there and the dr d theta. Be careful, a is a constant. A is just related to how big the shape is. So integral 0 to 2 pi. R squared is a squared times 1 minus cos theta squared. Dr d theta, because a is a constant, the a disappears when we differentiate it. Cos goes to minus sign, so it's a sine theta. We're squaring it. Okay, and then we've got a mess underneath the square root, so we can simplify that. The common factor of a squared for both the terms can be pulled out of the square root as an a and pulled out of the integral as an a. Expanding the stuff underneath the square root, we've got 1 minus 2 cos theta plus cos squared plus sine squared. Cos squared plus sine squared is equal to 1 for all values of theta. And we're therefore integrating square root of 2 minus 2 cos theta. Common factor of 2 can be pulled out as a square root and then pulled out of the integral. So root 2 a 0 to 2 pi integral of 1 minus cos theta d theta. Now, don't do all this work and then integrate this thing wrong. Okay, a really common student mistake is they'll go, well, that's also an error with a plus instead of a minus. They'll think because this is powered by a half, we just need to increase the power and divide by the new power. Sometimes students will go further and go, oh, I need to divide by the derivative of the inner function, which is sine theta. But that's completely wrong. It's not how the reverse chain rule works, and the only reason it works for NCA problems is because the inner function here is usually a linear function, meaning when you divide by its derivative, it gets you the right answer. We'd be in a bit of a pickle if we did this because our limits are theta equals 0 and theta equals 2 pi, and what are we going to do when we have to sub it into the denominator here? We're going to get division by 0, so nope, let's get rid of that monstrosity of a mess. To integrate this thing here, there must be a trick. Okay, and because it's trigonometry, it's probably a little identity that will help us. It's underneath a square root, so we're talking perfect squares here. It's got to be a perfect square. So if you look at the formula sheet, and you look at the double angle formula, the formula I'm going to use, it needs to involve a 1 minus cos theta. So there's a formula that says 2 sine squared theta equals 1 minus cos 2 theta. The only difference is the 2 theta. I want it to be theta, so I've halved the angle, so I half the angle on the left hand side. So 1 minus cos theta is 2 sine squared theta over 2. Got to decide, can I get rid of the square root and the squared? Do they just cancel each other? The sine graph, this here is the sine graph from 0 to 2 pi. Sine theta over 2 looks like that. It's always positive. And therefore the square and the square root do cancel each other off because we're dealing with a positive quantity. My point is, if you go square root negative 6 all squared, for example, negative 6 all squared is 36, and root 36 is 6. We're talking about the positive root. If you cancel those things off, you get negative 6, you get a different thing. So technically speaking, the square root of something squared is the absolute value of x. But if the x is positive, we can just knock the square root and the square off, as in this question. Okay, so those are little subtle details that sometimes trip you up in a problem, but we've got a root 2. We can pull that out as making that a 2. And we're integrating sine theta over 2. Sine and antidifs to negative cosine. The inner function, yippee yay, is now linear, so I divide by its derivative. Its derivative is a half, so I need to divide by a half. And I'm subbing in 2 pi and 0. Dividing by half is the same as timesing by 2, so we've got 4a minus cos theta over 2 between 2 pi and 0. Sub in the 2 pi, I've got negative cos of pi, which is 1. And then sub in the 0, I've got minus negative 1, so 8a. Now, does that seem sensible as an answer, 8 times a? Let's go back to the picture. It looks roughly circular. And if I go, right, that's 1, so a diameter of 5 for the circle. And pi times 5 would be the circumference of it. Pi times 5 is, about 15.71. We reckon that a is equal to, the length is equal to 8a, and this question's given us a picture with a is 2, well, that's 16. So we're in the ballpark. It's a really good way of checking. Okay, third question. We've got Newton's law of gravitation giving us this formula here. We've got F equals ma leading us to this differential equation. It doesn't look like a differential equation because it doesn't have a derivative in it, but easily can be made into one. Ma equals negative mg r squared x plus r all squared. Okay, a is the acceleration, and a is equal to dv dt. So there's your derivative, how velocity is changing with respect to time. The question talks about a rocket being fired vertically upward. Its speed is going to depend on time. Its speed is going to depend on gravity. Its speed is going to depend on how far away from Earth it is. Of course, as it gets further and further away, its speed is slowing down because the gravitational pull is making it return to Earth. Otherwise, the rocket would shoot off and get into orbit. Well, beyond that, head off to planets and whatnot. R is the radius of the Earth, because bigger bodies have bigger gravitational pull, and M is the mass of the object. So we've got a whole heap of constants here. We're assuming that when we shoot the rocket up, it doesn't lose fuel, therefore change its mass. So we can cancel off the m's on both sides of here, and m is a constant. We've got g as a constant, m constant, g constant. Gravity actually does change the further away or the higher altitude you are. I remember at university, the basement of the science building had a little plaque on the stairwell telling us what the gravity was at that particular point on the stairs. R is constant. So we've actually only got two variables here. A and x are variables. But when we make a equal to dv dt to turn it into a differential equation, we've now got three variables. And so how do we solve a differential equation with three variables? We don't just integrate. Okay, we could do that if the independent variable was x, because the right hand side's got x's in it, but it's not. We need to integrate with respect to time. So v is the integral of this stuff with respect to time. How do I anti-diff something that's got an x in it and no t's at all with respect to time? That's the tricky part of this problem. You actually need to realize that dv dt is dx dt times dv dx. The reason I've done it this way, I've used related rates, but I want to bring the x into the problem. And dx, it wasn't there to begin with on the left hand side. The other sneaky thing is dx dt is actually v. So dv dt, the left hand side, can be written as v dv dx equals negative gr squared x plus r all squared, and now we've got two variables. Okay, x and v are the variables, and we can separate it. Okay, so if I leave the v with the dv, put an integral symbol, bring the dx up the top, integrate that, we've got v squared over 2 equals negative gr squared, so that's just a constant, so it just sits there. We have x plus r to the minus 2, so when we anti-diff it, we want x plus r to the minus 1 over minus 1, and then we need a plus c somewhere. Okay, so v squared over 2 equals gr squared over x plus r plus c, because there's two minuses there. Now we go back to the problem. We need some information to find that plus c. We know that the initial velocity is v0. And initial velocity for this question is when it's on the Earth's surface. So when x is equal to 0 at time equals 0, we have a v of v0. We don't need time equals 0 in this because our solution doesn't have any t in it. So it's x equals 0, v is equal to v0. And then the question's asking us, when we get to a maximum height, so when x is equal to h, the v will be 0. Maximum height is when it's just turning around to return, so it doesn't have any speed at that point. And that's at some value of t, which we don't know, but we actually don't care about. So subbing in that first bit of information, x equals 0, v is equal to v0. Therefore, v0 squared over 2 equals gr squared over 0 plus r plus c. We can cancel off one of the r's there, and we get c is equal to v0 squared over 2 minus gr. Okay, then we go back to our solution. Our solution to this problem is this dude. Actually, no, I like it. The line underneath is much nicer. No minuses. And this time we sub in x is equal to h and v is equal to 0. So we've got 0 is gr squared over h plus r plus our c value. And the question tells us we're needing to prove v naught equals something, so we want v naught to be the subject. So v naught squared over 2 equals gr minus gr squared over h plus r. There's a common factor of gr there. And I can put these fractions together by making the 1 equal to h plus r over h plus r. That's gr times h over h plus r. Okay, times by 2 and square root. And that is the proof, my friends. Catch you in the next video.